Okay, so I want to prove that a scheme X is integral if and only if X is reduced and irreducible. So we start with the forward direction. Let's suppose X is integral. First, let's recall the definition of integral, reduced, and irreducible. So recall. X is integral. A scheme X is integral if for each open subset U, the ring over U is an integral domain. Then a scheme X is reduced if for every point P in X, the stock at P is a reduced ring, i.e. Has no non-zero nilpotents. And then a scheme X is irreducible if it is irreducible as a topological space. And the equivalent definition that we'll be using in this proof is any two non-empty open sets have non-empty intersection. Okay, so yeah, I'll go ahead and move this guy down here. Let's suppose X is integral. Then each open subset U of X has its structure sheaf, its ring over this open set is an integral domain. In particular, for every affine open subset, spec A as a subset of X, OX of spec A, which is equal to A, is an integral domain. So we can view, given a point P in X. Since X is a scheme, P is contained in some affine open subset. That's the definition of a scheme. Every point has a affine open neighborhood. So we can view the stalk at P as being isomorphic to the stalk at P over spec A. And this is just given by localization of A at P. We're localizing at a prime ideal, so everything but the prime ideal becomes invertible. And localization of an integral domain is an integral domain. So OXP is reduced. That's for every point, so X is reduced as a scheme. Now, to show irreducibility, let's suppose we'll use the contrapositive. Let's suppose X is not irreducible. Then there exists two non-empty open subsets with let's call them U and V, such that their intersection is empty. Now we can consider the union of these two open subsets as an open subset of X. And we can look at the set of sections, the ring of sections, over the union of these two open subsets. For each section in this ring, we get a restriction S restricted to U in OXU, and S restricted to V in OXV. And since this forms an open cover, since U and V are an open cover of the union of the two, and the intersection condition is trivially satisfied since they have empty intersection. The gluability axiom of a sheaf allows us to glue SU and SV together. And since they have disjoint intersection, and we can view S as the compatible germ consisting of S restricted to U and S restricted to V. And this is true for every S in OX U union V. So there's a natural isomorphism. There exists an isomorphism of this ring of sections with the product, we'll call that one U, of these two set of sections, rings of sections. And this is clearly not an integral domain. Not an integral domain. Since it has zero divisors. SU 0 and 0 SV, for instance. So by contrapositive, via the contrapositive, if X is integral, then it is reduced and irreducible. Now for the reverse direction, let's suppose X is irreducible and reduced. Okay, so I'm going to break this up into two steps. First, I'm going to show that an arbitrary affine open set of X has its ring of sections an integral domain. And then, since it'll be an arbitrary affine open set, from there I will show that an arbitrary open set of X must be an integral domain. And to do that, I will use the contrapositive. Okay, so let's take some affine open subset, spec A, in X. Okay, so it's pretty clear that any open subset of an irreducible set or topological space is irreducible. So let's suppose Fg is equal to 0 in A, and without loss of generality, suppose f is non-zero. Well, let's see. We have that for each point in the stock, for each p in the non-vanishing set of f, we have f spec A multiplied by g spec A is equal to 0. Some u subset. Well, in fact, this is true over spec A. So we have this is true in the stock over P. And at each one of these P's, we have f is not in that prime ideal. In other words, well, f does not vanish at any one of these points. Since P is in the does not vanish set of f, which is a basic open set, f does not vanish at P, and therefore f spec A is a unit. And thus, don't need a comma there. G spec A is equal to 0, spec A. In other words, for each P in DF, P is in V of G, and thus D of F intersect D of G is empty, right? But X is irreducible, or in particular spec A is irreducible. So it must be that D of G is empty, i.e. G is a nilpotent of A, and therefore a nilpotent in each stock of A, but A is reduced, X is reduced, spec A is reduced. So we have no non-zero nilpotents. Spec A is reduced. Since X is reduced, so there are no non-zero nilpotents. So G is 0 in each one of the stocks. And therefore, by gluability, G is 0. G equals 0 in A. So A is an integral domain. Now for the last step, we're going to use this lemma. If X is an irreducible scheme, and each spec A is integral, i.e. each A is an integral domain, then X must be integral. And we will do this via the contrapositive. So let's suppose X is not integral. Then there exists an open subset of X where OXU is not an integral domain. And we will show that then there must be an affine open subset of U that is also not an integral domain. The ring of sections over this affine open set is not an integral domain. Okay, so since OXU is not an integral domain, there exists F not 0, G not 0 in OXU with F times G equal to 0. Now, I have proven in a previous exercise that the subset for which F does not vanish is open. So let's call U sub F the subset where F does not vanish, and U sub G the subset where G does not vanish, are non-empty and open. Since F and G are non-zero, and UF intersect UG is non-empty. Since x is irreducible. Since affine open subsets are basic open subsets, there exists a spec B that is contained in the intersection here. And F restricted to spec B times G restricted. I'll go ahead this. F restricted to spec B and G restricted to spec B are non-zero, since this is a spec B is a subset of the non-vanishing subsets of both F and G. But they're equal to FG spec B is 0. And so B is not an integral domain. Thus, we have x reduced and irreducible implies x is integral.